But thank you for the organizers. It's been a great event so far, and it's great to talk to you. So for those who don't know me, I am a postdoc in Aki's group, and this is also a work with a lot of the people in the group. So Noah's in the audience, Jan is in the audience, and Aki, I guess, somewhere too. And so in this project, we were concerned about how priors are formed for, very foundational, time series models like AR with covariates and so on. And we thought that we should be able to motivate a prior from something more interpretable than the coefficients in such models. In this case, the R squared, so the coefficient of determination. All right, and so to motivate why this is actually an important thing also in time series models, what I've done here is I've generated prior predictive R squareds, so generating from your coefficients and then seeing what the implied fraction of variance explained is from a very simple AR model, and I increase the number of lags, so that's referred to as the AR order. And what you'll find is that with simple Gaussian priors in this case, if you have more than, say, 9 lags included, your model is saying I can explain 100% of the variation of the data. Now, this is a quite unintuitive thing to assume because particularly in stationary time series models, we usually assume that the first couple of lags matter, and after this, not much can be explained anymore. And so after a significant amount of lags, we shouldn't want to explain more and more variation of the data. So we want to kind of limit how much we can explain with the lag order that we include modeling. And so this work is actually quite simple, what we want to do. So we identify the culprit, which is that the coefficients in time series models are often assumed to be independent. And what this does, it lets the prior R square explode as you increase the number of components included, in this case, AR, lag orders. And there have been solutions in the past now, past couple of years, for data which is assumed to be independent. And two notable mentions is then the ARR2 paper from Zhang and co-authors, and then also Javier and Paul have been working on how to extend this to situations in which you have hierarchies. And what we've identified is that this hasn't really been addressed for time series models. So this is what we want to do. And so we derive, first of all, what the R squared looks like for ARX, so that's including exogenous covariate information, and then finally state space models. We will discuss how you might tune this prior according to how you think the time series correlation structure looks like, and then particularly how you might motivate it from other priors. And then we also have some code publicly available. But my goal for today is not only to dive into the mechanics of the prior, but also I'd like to hear from you guys in the end perhaps where we could improve on what modeling things we should address, and perhaps also how we could implement the code in some package or another to make it more widely accessible. So let's go with that. Okay. Right. So let's try to fix ideas with the model we want to form the prior over. So we assume that we have some outcome yt, which is modeled by a linear predictor containing 3 different components. One is just like a simple linear regression type component. One is something that models the lag correlation structure. And then one is then the contribution of the states. And so states here are just an unknown vector which has its own AR process. So this is kind of standard time series analysis stuff. So factor analysis, structural equation models can kind of fit in this kind of framework. And so we'll assume throughout that the observation model is always going to be Gaussian. And one thing I'll use quite often now in the presentation is that I'll denote the variance operator for a variable x by the sigma square underscore x. So let's keep that in mind. And we will define the R squared, the coefficient of determination in just simple linear regression models, as the variance of this predictor term that doesn't include the noise over that same variance plus then the noise of the observation model. And what we want to do is assume that we set normal priors for the coefficients appearing in this what's called observation equation, so the betas, the phis, and the states. How can we formulate the scales of these priors such that they imply a certain prior knowledge on the R squared? And then we kind of want to encapsulate the information on the R squared with a beta distribution because it's naturally defined over 0, 1. And the way you can perhaps understand this prior generatively is that we first have some idea of what the variance explained is, the R squared. This determines the total variance of the model. Think of this as like a global scale, which is shared by all unknowns. And then we want to decompose it with weights. And these weights then live on the simplex, so we just assume that they sum to 1 and are positive. And this is the crucial aspect. So this decomposition will encode some dependence between all of these modeling blocks. And the time series literature so far has been going with independence between these modeling blocks. And this is actually the reason why R squared is exploding in those kinds of models. So then after you decompose the total variance, this then forms local scales. So if you're familiar with the global local type framework, then this is the scales which are then individual to each unknown parameter. And these then generate the unknowns that feature in the observation equation. All right, so let's make it more specific to the AR model. So in this case, then the linear predictor term is just the past observations with unknown coefficients phi. And if we follow this R square recipe, so if we derive what the R square looks like and formulate what is the implied distributions on the scales, and we will find that, and this is very similar to the previous literature, the global prior scale will follow beta prime distribution. So this just comes by a change of variables. And there are a couple of features I want to highlight here, and one of them is distinctly different to the previous literature. Well, one is that we have a scaling in the prior by the observation noise, and then a noise term which depends on the data itself. So this is needed in order for changes in either of those so that the R squared stays constant. Then there's dependence, which is established via this decomposition term, the weights. So this is the size. And where our time series knowledge will be encoded is at this level, namely the concentration parameters for the weights. And I will go in one slide later what that actually means. But the specific thing about the time series model is that this conditional variance term is determined by a set of simultaneous equations called the Yule-Walker equations. If you don't remember them or don't know them, what we do also in our paper is that we take a database estimate, so you don't have to try to solve this with each iteration of the sampler. But this then is kind of the point of departure compared to previous versions of the RTD2 prior. All right, so then at this point, you might ask, well, this is nice and good, but how can we now encode our time series knowledge? And to visualize how you might think about this, we have two knobs that we can turn here. One knob is the prior on the R squared. So this is the distributions I'm referring to up here. And then we have another knob which we can turn, which is the prior concentration values of the Dirichlet. And these determine the relative importance of the lags. And so here we've generated prior predicted distributions for the R squared and the relative importance, which we define here as the relative R squared, or just the variance of one lag over the total variance of the model, and doing this for all lags. And I want to just highlight a couple of things at this point. So one is these two things are entirely independent when you set up the prior. So you can have, like here, the ARR2 is set up to have a beta 1/3 3 prior, has like a very gentle slope just to kind of penalize more toward the low R² region. But you can do just a simple uniform prior. You can have some kind of bathtub behavior, which would give you some nice theoretical properties. But compared to what the literature uses, which is, for example, the regularized horseshoe prior in, I guess, purple, it penalizes heavily toward low R², and this is with a prior guess on the model size of half of the number of lags included. We have something which is used quite a bit in the social science literature, the Minnesota prior. What this one does is it penalizes the lag order inversely proportionally. So the further you're going down the lag order, the more you penalize. And this is also very informative in R² space. And obviously, then independent Gaussians are generally a bad idea for AR models. And so the second point about the relative importance is that we can mimic any behavior of other priors in terms of specifying which lags matter in exactly the same way. So if the Minnesota says that the first lags matter a lot and then decrease the level of importance, we can do the same thing with the AR2 by just specifying the concentrations in a certain way. If we want flat import, so such a uniform measure of importance across the lags, we can do that. And we can also encode other things like a hump shape behavior. Maybe you think that initial lags don't matter, but then lags in four lags down the road, they matter again. So all these things can be encoded separately to your prior on the R². All right, so that was a pretty simple model that we looked at, right? The AR models. Let's kick it off a notch, look at state spaces. So here we'll make the simplifying assumption, since we just talked about lags, that we do not include them. It's just extra predictors, which are indexed by time, and then a state contribution in the observation equation. And then each state has its own AR process. What happens if you go through the machinery that we have in our paper is that you get something like this. So this is now the prior for state Q at time t, conditional on the same state one time step back. So you can think about this prior as essentially setting up a series of conditional priors. And there are a lot of things going on here, so I want to kind of go it one by one. So what happens if you set a prior in R² is that you have three different terms. One is that you have to scale again by the noise variance. This is entirely a departure from the previous state space literature, which always has assumed independence to the observation noise. But it should make intuitive sense to include it, right? Because as more noise is added to the data, you should also have more noise in the states that you're filtering out. You now also have dependence on the state AR parameter and this is now for state Q. This is telling you that if you're standing at time point t minus 1, and you have high serial correlation in the states, so a large AR parameter, then that should give you a lot of information about what happens in time point t. So therefore, the signal should increase as a function of the size of this AR parameter. And this is what's encoded now in the prior to. And then what we also have is that the states now fight in relevance for the model compared to all the other components included. So this means that the states can only explain the variation that the regression component cannot explain. Whereas previously, all these things were independent, and you could have ended up with a situation where the states and the regression component explain the same thing. All right. Of course, this is well and nice, but if you include more states, if you include more covariates, you're going to end up with a problem of trying to estimate a very high-dimensional simplex parameter. What would you recommend in those cases? Well, what we've done in the paper, what we experimented with is we grouped parameters such that within the group we have some deterministic way of decomposing. So if you have p lags for each of the covariates included for some reason, then you could think about forming a group at this level, and then within that decomposing by some deterministic rule. All right, so now let's look at some empirical evidence. So we have today now a set of experiments for the AR models, ARX, and then the LTX. LTX is just a simple state space model with one unknown trend included, and this unknown trend has a AR process. And we have some pretty simple stuff going on here. What we did want to do was put the ball into the Minnesota's court. So what we did is we generated the AR parameters according to actual Minnesota decay. So that's if we beat the Minnesota at its own game, then that's kind of a nice thing. And then we have two questions. So one is, since we're setting a prior on the predictive performance, so to speak, on the R squared, it should scale quite well with including complexity, including more variables. That's what we're going to investigate. And then how well does the framework adapt to low state signal problems? And this is a quite perennial issue because essentially deciding whether a state is important or not is a variance selection problem, and this causes a lot of issues. Well, here we're looking at log predictive densities, mean log predictive densities for increasing number of predictors for different amount of correlation in the covariates. What we can see quite simply is that we heavily outperform the Minnesota prior. And this is a quite nice thing. So we're looking at the AR2 version, which has Minnesota decomposition or flat. And what we find is that we're either very close to the best performer or doing very well. So that's kind of a nice result. And what we see is that this gap tends to get bigger also when you include more predictors. And this is something you would expect from an AR2 type of prior. Now, here we're looking at parameter recovery of the state standard deviation. So this governs how variable a state is from one time point to another. It's important to know what this is because you base selection on whether a state is important or not on this. And what we find is that, and this is root mean squared error, as the state's signal goes down, the AR2 priors get more and more important to include. So here, because we're putting into the modeling process this dependence, we're modeling the signal from the state, we're much better at recovering it also. And then this gets also reflected in predictions, where here we're looking at the mean log predictive densities. Here, though, in relationship to more and more time points seen. All right, and then we have a nice application to inflation forecasting in the paper. So this is something I've worked on before. Thanks. And I'll keep it very short. Essentially, we have a lot of covariates included. We have only one state, one unknown trend. And what happens is that priors that do not have a prior on the R squared will horribly overfit. And what this comes from is that the state's standard deviation is not well informed by the data, and then if the prior is too loose, this is what's going to happen. Prior and posterior go to 1, whereas we can regularize far away from it. And this is also reflected then in predictive performance. Here we have the cumulative log scores over the evaluation period. And what happens is that at certain time points, the priors which put too much weight on the importance of the trend completely miss where inflation is heading. And this is where then the AR2 priors do quite a bit better. Yeah, and then this is just because also less weight is on the trend. But okay, so what I want to end with is, first of all, that you can inform this prior by your knowledge of importance of lags and the time series structure. It's important that you know how to set this decomposition. And this can be informed by sparsity knowledge, by time series knowledge, even grouping structure. If you're not sure how to set them, you can always try to calibrate it vis-a-vis other priors, as we've seen that you can mimic essentially the Minnesota. And what I'd like to ask you is, are there things that you think we could particularly extend upon? And then, yeah, if you have any suggestions for where to include the code and stuff like that, then I'd be happy to discuss. Thanks.